All right, guys. So we have chapter 4, which is basically going to be on two-dimensional motion. So we're going to learn how to solve problems about motion in a plane, which means that our motion is going to be in both horizontal and vertical axis kind of combined simultaneously. All right, so some of the things that we're going to be learning in this chapter is pretty much like a repeat of whatever we learned in chapter 3 and 2. You just now we're kind of combining them with sort of like both dimensions, x and y. So remember, so this equation is for the average acceleration. And we learned that average acceleration is change in velocity over time. And it's a vector, and delta v is also a vector. So in a way, what we have here is the delta v as a vector, which means by how much velocity changes, right, is what the acceleration is sort of proportional to. It's always pointing in the same direction. So that's why whenever we have acceleration, then velocity will change. But velocity can change two different ways. Velocity can change when object basically changes the magnitude or the speed. So the magnitude of the velocity can change, indicating change in speed. But we can also have the direction of the velocity change. And that also changes velocity. So acceleration can then do two things. It can change the speed and it can change the direction, because either of those things are basically changing velocity. You can do both, right? There could be a problem where you are actually, have an object that speeds up or slows down and changes direction at the same time. So here's an example for, for the object at this point 1, let's say it has a velocity in that length, right, that direction. And then, let's say a second later, when it's this position 2, that's the velocity. Okay. Remember, this velocity means that, this green arrow, right, represents velocity at this instant. So that 1 over there represents that point. So the velocity, magnitude, and direction represents how fast the object moving at that particular instant of time. This velocity represents how fast it's moving at this instant of time when it's right here. So one of the things we can do here is, let's say, we can see that if I am combining that, remember, technically delta V here is V, let's say final, which in this case n plus 1, minus V initial n, right? Then I can represent it like this, where pretty much I'm adding them together, but the negative of Vn, right? So then it's a vector addition. And if that's a vector addition, then I'm adding Vn plus 1, which is I have over here, to the negative of Vn. That means this is the negative of Vn. And tip to tail then allows me to find change in velocity as a vector. Once I have change in velocity as a vector using this addition, then technically I also have the acceleration this direction, because acceleration always has the same direction as delta V. So that's why delta V and acceleration proportional to one another, meaning that they also have the same direction. All right, so now what we're going to be looking at here is the object that, let's say, all right, so starting from this point 1, starts moving, but then there's acceleration that changes its direction. So here's point 2, here's point 3, here's point 4. And you can see, right, there's a, direction change every time the object basically goes around in a circle. Okay. And acceleration vector is always pointing again in the direction of delta V. Okay. So this acceleration is actually responsible for right now changing the direction of the, velocity, right, of the object. And one thing you can see here is, it's always pointing toward the center, and object always, those green arrows, right, they're all identical in terms of their length, but they just have a different direction, which means this acceleration is changing the direction and not changing the speed. Okay. So we can then think of like acceleration as having two components, or like, let's say, not in terms of like X and Y, but sort of like, let's say it has two functions. Here's the acceleration as a vector. So you can think like this: acceleration relative to velocity can have a component that is parallel to the velocity and a component that is perpendicular to the velocity. So, right, so you can say, right, if I'm drawing acceleration vector, then it has, if I break it down, you can see, right, there's a parallel to the velocity component and there's a perpendicular to the velocity component. Each one has a very specific function. The one that is parallel to the velocity, we already worked with this one before. This is the one that changes the speed. In chapter 2, this is what we use basically. Okay, so this is the one that pretty much changes the speed. Okay, the perpendicular to the velocity acceleration, which is the component of this acceleration, right, is actually the one that now responsible for changing direction. And we didn't talk about this in chapter 2 because we assumed it's a one-dimensional where the direction doesn't change. But now you can say that acceleration has those two, parts, parallel to the velocity and perpendicular to the velocity. The parallel one changes speed, perpendicular one changes direction. So that's why an object changing direction always has a component of the acceleration perpendicular to the direction of the motion, okay, regardless if it's speeding up or slowing down. If, for example, you have an acceleration that only has, parallel component, that means object will never change direction, but can, speed up or slow down as in going, in a straight line. You add this to the, perpendicular component, then it's going to start, changing direction. If this is 0, let's say, perpendicular, parallel one is 0, but you have only perpendicular one, then what it does, it goes around in a circle while maintaining constant speed. Okay, we're going to see that this is known as a uniform circular motion. All right, so then we're going to then setting up our understanding of, let's say, a two-dimensional motion, because now the object can also, move such a way that it's not only changing position in the X or changing position in the Y, but X and Y combined, that means simultaneously. And here's an example. So for example, this graph where you have Y-axis versus X-axis, this is not one of those position versus time. This is Y versus X. That means this blue line over here, which now I'm going to make it as a red, right? So this red line here actually represents the trajectory of the particle's motion. That's the trajectory of the object. That's how it's moving. Not some abstract position versus time graph, but it's actually how it's moving in space, so let's say. So one thing we can do here is this. We can choose one point. Here's point 1. And I'm going to say that's my starting point. All right. Then with respect to the origin, we're going to draw a vector from the origin, our reference point, to that point 1. And that's basically this R1 vector from the origin to that point R1. Then the object, let's say, moves, and I'm going to take another point of interest, which is this point 2. Right, so the point 1 and point 2. Okay. And then what I'm going to say is that that's my final point. Point 2 is my final point. Then I'm going to draw a vector, again, from the origin all the way to the, point 2. And that's R2, which is my now final position vector. Okay. Then what I have here is this. If I then connect point 1 and point 2 directly in a straight line, which is what this delta R represents, then what I have here is basically this, right? Delta R represents changing two-dimensional position. Sorry about that. So delta R here is changing, two-dimensional position. Okay. Now, one of the things you can see here is this. I created technically a triangle where I have R1, position vector R1, and then you can see, right, the delta R is technically connected to R1 such that tail of delta R is connected to the tip of R1. So, mathematically speaking, then delta R plus R1, right, is then will give me R2, because R2 goes from the tail of the first one to the tip of the last one. So then this is equals to R2. Okay, delta R plus R1 equals R2, which makes sense, right? Because if you have this position vector, and then you add by how much it will change, then what you get here is that then we have a final vector. But generally what we do for this one here, we can then rewrite it as delta R equals R2 minus R1 by moving the R1 to the other side. Which means as we work with those three vectors, right, delta R, R2, and R1, we can see that changing, R is equivalent as difference between vector R2 and vector R1. So vector R2 minus vector R1. Okay. Now, another very important thing here to understand is this. Delta R, which is basically this vector here, right? Let me put it in black so you guys can see that. This is delta R. This is also, it's my displacement, right? Now, what I have with that is this. When I have that change in position, right, it is actually two-dimensional, which means I can look at it in terms of here, right? So you can see, right, I can look at it in terms of x1 and x2 and say that, as the object goes from point 1 to point 2, this is by how much its x position changes. This is my delta x. Same way, going from here to there, I can look at this in terms of as how my delta y is changing. Okay, that means, for example, then delta r is equivalent, right? Because if I do this as a delta x, and this is a delta y, so you can see, right, going from point 1 to point 2, like along the delta r, right, is equivalent to saying that there's a delta x and delta y combined, because then delta r is changing position of the x plus changing position of the y together. That means the sum of those two is equivalent to this delta r. Okay, then I can in a way write it in terms of unit vectors, which is I always prefer, right? Then I can say delta x I hat plus delta y j hat. And that's my equation for the two-dimensional position change. So that's why I think like this. If object is only moving in one direction, that means this is probably 0, so you only have a change in x. Or if it's going straight up, this is 0, and then you have just changing y. But if it goes such that it's changing both horizontal and vertical positions, then you have to look at delta r, okay? What if we measure the time as the object goes from 1 to 2? Then what I can do here is I can take the delta r and divide by delta t time interval. What do we get? We get v average. Well, since then delta r here is the sum of delta x and delta y, then I can say it's delta x over delta t I hat plus delta y over delta t j hat. That's what the v average then technically represents. All right, so then again, I have then this delta r, right, which is delta x, or in delta x I hat plus delta y j hat, right? Then I have then v average, which is then delta x over delta t I hat plus delta x over delta y over delta t j hat. Okay, clean that up a little bit. So delta y over delta t j hat. Now, technically, this means there's average velocity in the x direction. This is average velocity in a y direction. And the way I would find the average velocity is by taking, let's say, point 1 and point 2, drawing a secant line, finding the slope, and that's the average velocity. But what if I want velocity that is not between those two larger time intervals, right, t1 and t2, but a little bit more specific, for example, smaller time interval or smaller time interval, or just at one specific time, right, let's say time, instant of time. Then this graph becomes, shorter and shorter and shorter until basically I have something that is tangent to the trajectory, and the tangent to the trajectory of the object motion then actually is the instantaneous velocity. You can see, right? Instantaneous velocity vector is tangent to the trajectory. And mathematically speaking is the delta r, delta t, and the limit where delta t approaches 0 and becomes the derivative, delta r over delta t. But since delta r is, delta x plus delta y, so this becomes technically dx dt I hat plus dy dt, j hat. Now, what it means here is, if I have then this velocity, delta x, delta t, then nothing but vx. So that's what it is. Delta y, delta t, nothing but vy. That means I can kind of write it like this, which means if I want to find x component of the two-dimensional velocity vector, I only need to look at horizontal position change. If I'm looking at the y component, I only look at y position change, basically the derivative of the position change in y direction as a function of time. That means I cannot say vy equals dx dt. It doesn't work like that, because vy only, basically how fast you're moving in a y direction, right? Remember, the velocity is a rate at which you change your position. If you change your position in a y direction, you have to look at it in terms of vertical velocity, right? Because that's what, responsible for changing your position in that direction. So again, if I then take a trajectory of the object and draw a tangent line at some instant of time, then I find instantaneous velocity, for that time. Okay, but still, it's a two-dimensional velocity. So one of the things I can do here is I can take that velocity, break it down into components. Okay, so basically, what is the direction of that velocity relative to, let's say, horizontal axis? So then I can find those two components, and that's always, very useful because nobody wants to work with the two-dimensional velocity vectors. Nobody, or any type of two-dimensional velocity. So that's why if I have delta r, I don't want to work with delta r. I would much rather work with x and y together, but let's say two one-dimensional vectors than working with a delta r. Same thing with velocity. Even if it's instantaneous, I don't want to work with two-dimensional. I want to work with, one-dimensional vectors. So we take it and break it down into components. Or also things like this. If you have the components, then you can use the Pythagorean theorem to find the magnitude and the direction, right? We'll learn about that in chapter 3. Because if you have the component of any vector, then you have two equations to give you the speed, which is the magnitude, and the direction of those vectors. All right, so now, again, going back to this trajectory of the object as it goes from point 1 to point 2, then one thing we can do here is to find velocity 1 and find velocity 2. Now, one of the things we have here is you can see that as the object goes from point 1 to point 2, it changes direction, which is obvious from those velocity vectors. But it also changes the speed because v2 is shorter than v1. Now, if we do, let's say v2 minus v1 as vectors, right, to find delta v, which is, v2 plus negative v1, which is, what this diagram represents, we can see that this is the direction of change in v, which means that that's the direction also changing, of average acceleration. Okay. Now, acceleration then, if I take that and break it down into perpendicular and, let's say, parallel, I can see then technically there's this a perpendicular and then there's a parallel. So that is why, for example, when the object is right here moving with this velocity, right, it has acceleration perpendicular, so it changes direction, and acceleration parallel, but it's in the opposite direction of velocity. So by the time it goes to point 2, it actually moves slower. That's why, because the acceleration can tell you, if it's going to speed up or slow down when it goes from point 1 to point 2. All right, so that's why, let's say, if I go and look at that, particular velocity, right, somewhere in between, I can see that that acceleration, is indeed, such that it makes it slow down and it makes it change the direction, right? Because again, if I break it into those components, I can see that. So now I can also do it in terms of, let's say, X and Y, since this is X axis and this is the Y axis. If I have that acceleration, I can find its X and Y components, just like I have the Vx and Vy, right? And Vx and, Vy over here. So that's why you can see, right? In a way, this acceleration has a Y component, which means this guy will change. And it has an X component, which means this guy will change, okay? So for both of them, it's actually gonna slow down. So that's why, for example, when I look at then this point, right? Over here, my velocity like this, and it will be shorter in terms of both of them. My Vy will change and my Vx will change. And technically over here, my Vy actually will be completely 0. But Vx, we know at this point not. So then when I do it like this, you can see then, you still have Vx and Vy, but now Vy is actually changing the direction. All right, so that means, we have that option to do the X and Y components of acceleration. Now, because, right, if Vx and Vy are the X and Y components of the velocity, then we can, look at the rate at which they're changing and find then the acceleration. That means Ax is equals to dVx dt, and Ay is equals to dVy dt. because only horizontal acceleration can change your horizontal velocity, and only vertical acceleration can change your vertical velocity. That means, for example, if you're writing acceleration as ax I hat plus ay j hat, then you want to see if, if they're zero or non-zero. For example, if you have an acceleration, which is 2 meters per second square I hat, but let's say plus 0 j hat, it means there is a horizontal acceleration, but no vertical acceleration. That means it's only going to be speeding up in an x direction, but whatever velocity you had in a y direction, right, it's going to remain constant over time. All right, so basically what we have is this. Acceleration is a two-dimensional now, x component I hat plus y component j hat. And if this acceleration constant, right? So let's say if a is constant, then that means the components are constant. And remember, we want technically to have a motion where the accelerations are constant because it's easier to work with constant acceleration. We can use all of those kinematic equations, right? So in chapter 2, we'll learn about those kinematic equations, but we kind of looked at either, in an x direction or either in a y direction. But here in this chapter, we can actually look at two-dimensional motion. That means, in a way, what we have here is if there is a which is constant and it has x and y components, that means they're also constant. That means I can separate the motion into just horizontal or just vertical. Look at those as separately, right? Just horizontal or just, that means treat them independently from one another. And I can basically solve horizontal separately from vertical, knowing that always delta t is one thing that connects them together, right? And then at the end, just basically put them all together back if I need to. That means I have two set of equation in the x direction, which is this one over here, and in a y direction, which is this one over there. That means I can look at each one independently from one another, okay? But, obviously always there's delta t here. Whatever is delta t here is the same as delta t over there. But for example, whatever delta x I have here might be completely different from a delta y over there. The only thing those two sets have the same, right, is if you have, talk about, like, let's say time interval. Only the time interval is true and the same for both of those, equations. Let's look at an example here. We have a sailboat that is traveling east at 5 meters per second. A sudden gust of wind gives the boat an acceleration of, and we're given acceleration in terms of its magnitude, 8 meters per second square, and direction, 40 degrees north of east. All right. So let's see what we have. It's asking what are the boat's speed and direction 6 seconds later when the gust subsides. All right. I have a diagram here for you guys. So assuming that we take the object, which is the sailboat, and let's say we put it exactly where the origin is at the t equals 0 time, then what we have here, our known values are this at x naught, y naught, or t naught, which are the initial values and positions, right? They're all 0. That means we start from that. But we also given that to start with, by the way, v naught is the same as v initial. So sometimes you might see them using either one. So what we have here, this is a two-dimensional vector, right? I have, this is, let's say, vx I hat plus vix I hat plus viy j hat. But we are told that there's a 5 meters per second I hat, which is east, right? But 0 j hat. That means initially the sailboat is moving just in a horizontal direction. But then there's an acceleration, and this acceleration is 8 meters per second square, 40 degrees north, which means it's basically ax I hat plus ay j hat. Which means then this is the equation that I have for the acceleration. It's a two-dimensional acceleration because if I look at this acceleration, I can break it down into components, right? So this one over here. So I can say then it's, ax is nothing but a cosine theta, and ay is nothing but a sine of theta. And I can find this acceleration vector then. So a here is 8. Actually, I do have a typo here. This is actually 0.8. So the acceleration is 0.8, sorry. So it's 0.8 meter per second square. So that basically becomes 0.8 cosine of 40, okay? Then I had, then plus 0.8 sine of 40, which means then my acceleration is 0.613 meter per second square I had, plus then 0.514 meter per second square j hat. So that's my acceleration, which means that I have ax and ay. So whenever I started with my initial velocity, right? This is my initial velocity of 5 meter per second I hat, then plus 0 j hat. So you can see, right? I'm gonna then start changing both of those, because this is by how much, each second the x velocity will change. This is by how much each second my y velocity will change, right? Now, the calculations for this, you could do two different ways. As I mentioned, you can separate each one into two groups. Just look at everything in x direction, or look at everything in a y direction, and then combine them together. That means to find v final x and then v final y, and then put them together. But you can also use the kind of like the combined component method. For something this simple, actually, using just the component method direct calculation might be a little bit simpler. That means what I have here is this. I can say then, let's say v final, remember the equation is v initial plus acceleration times time. This is the vector format of equation 1 of kinematics. And I can say v final is equals to v initial is then 5 meter per second I hat plus 0 j hat, then plus, then my acceleration 0.613 meter per second square I hat plus 0.514 meter per second square j hat, and times time. Well, time here, remember, is 6 seconds, right? So we're given the times as 6 seconds. So then I calculate this to be then 5 meter per second I hat, then plus, well, let's say 0 j hat, I can do that, right? Then plus, and then 6 seconds times 0.613, or 6 seconds time, and basically I kind of, distribute that, right? So I can just basically calculate those together. So what I will get here is 3.68 meter per second, because if I do seconds times meter per second squared, units cancel out one of the seconds, right? I had, then plus, and then here I'm gonna get 3.09 meter per second j hat. Okay, that means this is basically over here in what I have in the parentheses. All right, so then I can see that I can combine I hat terms and j hat terms, which then will give me 8.68 meter per second I hat, and then plus 3.09 meter per second j hat. So this is my then v final in terms of its components. And then we learned that if you have a vector with components given, then I can calculate the magnitude which will be square root of 8.68 square plus 3.09 square, right? That means using the Pythagorean theorem to find the magnitude, which is going to give me 9.2 meter per second. So that's the magnitude, that's the speed, right? Because we were asked for the speed, that's the speed. And I can use the inverse tangent to find the direction, which is 3.09 divided by 8.68. So I get 20 degrees. That means it's 20 degrees, you can say north of east. Okay, and that's my answer. That means by the time it gets here, the velocity here has a magnitude of 9.2 meter per second, 20 degree above the positive x-axis, or 20 degree north of east. All right. Here's one more example. We have a particle's trajectory is described by x equals 1/2 t cubed minus 2t squared meters, and y equals 1/2 t squared minus 2t meters, where t is in seconds. And I guess, like let's say you can say the distance is in meters. Okay, so for part A, so this is basically, in terms of part A, right? We want to calculate what are the particles' position and speed at time t equals 0 seconds and time t equals 4 seconds. And then part B, what is the particle's direction of motion measured as an angle from the x-axis at t equals 0 and then t equals 4 seconds. All right. So now what we're given here is object moving such way into dimension that, sorry, this x as a function of time is given as 1/2 t cubed minus 2t squared. And then y as a function of time is given as 1/2 t squared minus 2t. That means this is my two-dimensional motion where every dimension basically is different as a function of time. First, we want to find what is the particle's position at t equals 0, which means that right now I can take this x and plug in 0 for time and solve basically 1/2 0 cubed minus 2 times 0. So I get 0. Same thing for the y. So 1/2 0 square minus 2 times 0. By the way, this was square over there. And here I get again 0 though. That means that's my position. So that means you can say that R initial is 0, 0. Or let's say, we can be more, in terms of like 0 I hat plus 0 j hat. I like to put it in terms of sign, let's say this unit vector notation. All right, that means at initial time, we're at the origin. All right, so then how about the, the second one, which is, when x and, when the time is 4 seconds. So we plug in 4, which is then 1/2 4 seconds cubed minus 2 times 4 seconds squared. So for this, what I get is this. So for 4 seconds cubed is 64. So then 1/2 of the 64, then minus 2 times 4 squared, which is 16. So half of 64 here is 32, minus 2 times 16 is 32. We get 0. All right, that means, 4 seconds later, the x position is also 0. Then I have y as, at 4 seconds. Then I have 1/2 4 seconds square minus 2 times 4 seconds. So then I have 1/2 of, 16 minus 2 times 4 is 8. So then what I have here is half of 16 is 8 minus 8, I get 0 again. Well, that means, our final is also 0 I hat plus 0 j hat. Now the question is that, does it mean the object never moved? So technically from here, we're not going to be able to say anything. To find that, we need to go and look at the speed at those times. And then we can figure out if it was moving or it was at rest for the entire 4 seconds. Okay. But to do that, we need to find the function for the velocity for the time as a function of time, basically. That means what we do here is I use Vx to find dx dt, and that's the derivative of the x with respect to time. So what I'm going to get here is then I'm going to take the derivative of that to get 3/2 t squared minus 4t, that's for the x. And then I have dy, which will be then dy dt. Hopefully you know how to do the derivatives for those parts, right? So it becomes 2 over 2, so it becomes just t minus 2t gives me just 2. That means those are my velocities as a function of time for x and y. Then I take this, remember I want speed also at t equals 0 and t equals 4. So first let's look at in terms of 0. So I have Vx at time of 0. So it's going to be 3/2 times 0 square minus 4 times 0. So I get 0. That means x component is 0. All right, so how about y component? Well, it's, 0 minus 2. Well, we actually get minus 2 meters per second. That means V initial as a vector had 0 I hat, but minus 2 meters per second j hat. That means our position was origin at t equals 0, but we were not at rest. We were actually moving, and we were moving straight down at 2 meters per second. All right, so that means there was a motion. So then let's look at the same thing in terms of the V final, right? Which is basically this was V, in terms of like 4 seconds. So this will be then 3/2 4 seconds square minus 4 times 4 seconds. So then 4 seconds is, 4 seconds square is 16. Then half of 16 is 8. 3 times 8 is 24. minus 4 times 4 is 16. So I get 8 meters per second. This is in the X. Then V final, Y direction, I guess, it's 4 seconds, right? So I get then 4 seconds minus 2. So not 4 seconds. So it's 4, so technically there's a 1, which is basically meter per second. So basically 4 minus 2, so I get 2 meters per second. And then you can say that my V final here is 8 meters per second minus, so plus 2 meters per second, J hat. This is I hat. All right, so those are my velocity. So this was my position, and this was my velocity in terms of those. Now, what I can see is that if I'm calculating the magnitude of the position, I'm going to get 0 initial, and final is also I'm going to get 0. Okay. But then I also need to find the, remember it's asking for speed, so I need to know what is the speed of the initial, which is, square root of, right? Square root of 0 square plus 2 square, so I get 2 meters per second. So speed of the final position will be then square root of 8 square plus 2 square. So then calculate that, and I should get 8.3 meters per second. Okay, that means those are the speeds for those. Okay. Part B, all right, so part B is then asking me to find particles' direction of motion as measured in terms of angle of the, with respect to x-axis, so t equals 0 and t equals 4 seconds. All right, so I can do that. So let's say here's my coordinate system. So I know one thing, that initial velocity, right, is this guy over here, is 0 I hat negative 2 meters per second. So that means something like this. This is my VI. That means it was moving down at the t equals 0. Magnitude of the final velocity, I have this 8.3. But what is the direction? Well, I can use this inverse tangent where it's 2 over 8, and I can calculate this to be 14 degrees with respect to positive x. That means the velocity final is 8.3 meters, which is, about, a little over 4 times longer, and 14 degrees. So let's mean something like that. Okay. Maybe even more than that, in terms of like longer. But this is, let's say, 14 degrees. That means in a way, this particle motion can be more or less described like this, going down initially and then probably turn around and started moving like that. Okay. So that's why it's coming back to the origin 4 seconds later, but it is moving in a different direction. It ended up basically making a round trip. So it moved down, then turn around, then come back and moving like that. Because it cannot be doing something like this, because here the velocity would have been like that. That means that would have been wrong. So this is probably the trajectory of the particle.